over it quickly using our 2-minute time limit, and then I'll explain a bit behind it, and then even explain a little about one of the compounds involved in this, which is interesting, potassium chloride. This was a part of a series of questions using this prompt. Some MC questions have got a prompt that you read and then use the information from it over a series of questions. On an MC exam, these will all be visible if you've got your booklet open. You won't have to flip back and forth unless you have to go to the equation sheet or the periodic table. So you would have read this ahead of time and then gone through the question itself. The prompt that is used has an equation, potassium and chlorine reacting to make potassium chloride, and they give you the enthalpy change for the reaction. They describe the reaction, and then they give the data for the reaction done in a series of steps, the Born-Haber cycle. All these steps involved in this reaction. You would have read this ahead of time. Right now, let's start our 2-minute timer and read the question. Which of the following expressions is equivalent to the change in enthalpy for the reaction directly above this question? So here's our reaction. Chlorine, 2 electrons, and getting 2 chloride ions. This is the electron affinity where we're forming the ion. This is a reduction reaction. Let's go to answer this question. We need to find about this reaction, and we look at what we're given here. And here I see that we have 2 equations that are similar to this that I'm going to use to answer the question. I'm looking at my answers. They're adding the enthalpies for these 2 reactions and which one of these combinations is going to work. I've got these 2 equations on the side. Here we've got the first one, chlorine making ClX, and then Cl gas making the chloride ion, and I'm comparing that to the equation that I want. And the equation that I want has 2 electrons as reactants and 2 chlorides as products. And I see here I've got an equation with 2 electrons. Well, with only 1 electron. So I need 2 electrons. Not this equation, but rather this one, doubling it. So if I double the reaction, I get my 2 electrons and I get my 2 chlorides. And of course, I'm going to have to double my enthalpy of reaction. And I say, wait a second. That's going to give me my 2 chlorides and 2 electrons. Do any of my choices have that option? And I look at A. No, that just uses Y. It just uses Y. Here's C. It's got a double Y. That's the only one. So this has got to be the answer. So that's it. We've got the answer to this question. Within our time limit, you can go on. But now let's just see if this really works. And I'm going to get I'm going to see indeed if these 2 reactions add up. I've got chlorine gas. Yes, here's chlorine gas, one of them. And it has 2 chlorine atoms. We've broken apart this diatomic gas. Now, there's no 2 Cl's in the reaction I want, but that's fine because if I add these 2 equations, it cancels out the 2 Cl's. And all that I've got left is chlorine, indeed, 2 electrons as my only 2 reactants, and then 2 chlorides. So if I double Y and add it to X, I would get the change in enthalpy for this reaction. With enthalpies, we add whenever we add equations, or if we reverse them, we change the sign, or if we double them, we double their amounts. And that's not true for equilibrium expressions, which you would have to multiply and square. So that's the explanation. But let's go to this entire reaction, because that's used quite often in AP exams. This is the Haber process, where we take the elements involved, in this case, the elements that make potassium chloride. This is almost always used in making ionic solids. So an ionic solid's got a metal, in this case, potassium, very reactive metal. You'll never find it naturally because it reacts instantly with water. Chlorine, another very reactive substance that you don't want to be around. To make salt, which is a very, very common mineral. This is an exothermic reaction. negative 437 kilojoules. The salt that's produced has strong ionic bonds. The metal and the gas have weaker bonds. So we end up having stronger bonds, which we always have for an exothermic reaction. Also, the enthalpy of our reactants, I mean, potassium and chlorine, they've got lots of potential energy. You can do explosions with these, all sorts of reactions. But the potassium chloride salt, I mean, it's the salt of the earth. Not much is going to happen with it. But let's look at the process. On this AP multiple choice exam, this one prompt on the Haber cycle had 5 questions on it. So that was 5% of the exam. So let's go over each of these steps to understand what this Bosch Haber process is all about. Matter of a metal and a nonmetal reacting to make a solid. And rather than just viewing it as one step, you break it apart into starting off by taking this metal, because we're ultimately going to change it into potassium ions, which is a solid, and break it up into a gas. So that has to be an endothermic process, and I'll put this in right now. We're breaking bonds. We're separating atoms. And these originally had metallic bonds, and now they're just free from one another. They are not attached anymore. The next step takes this gas and rips that electron off of it. This is what we're going from the gas, and now to make our ion. We're on our route again to make potassium ions. And again, it's a process where we have to take an electron, which is attracted to the nucleus of the atom, that it must be an endothermic process also. All ionizations, removing an electron from an atom, are definitely endothermic. So far in this process, getting our potassium ions required an investment of considerable amount of energy. The enthalpy change would be positive. The enthalpy change would be positive. We had to put kinetic energy into this thing to create these new substances with higher potential energy. Now we have our potassium ready to make our potassium chloride. Now we've got to get our chlorine. Now notice this reaction that they gave on the exam had a full Cl2, but we need to have a half of a chlorine. So in this case, we're going to have to take this reaction, not leave it as it is. Without doubt, we're going to have to put a 1/2 in front of here that will change this to 1/2 of a chlorine in our desired reaction. Of course, that means that we no longer have a 2 here. We've got a 1Cl. And let's not forget that we needed to take this 1/2 and put it into this X because we only need half as much enthalpy. Now, again, this is a case where we're breaking bonds. We're taking 2 atoms with a covalent bond, diatomic chlorine. Remember, that's one of the first things we learned in AP Chem about the diatomic nature of chlorine, something that you've got to remember. And this is endothermic, without doubt. And so far, we're in a hole in making our ionic compound because we've had to invest a huge amount of energy to get our potassium ions. Oh, we're not with chloride ions. We've got chlorine gas, separate atoms. So we're going to give them an electron to make them chloride. Now, this is our first chance of actually making a bond. This electron is going to be attracted to the protons of the chlorine, which are there, and that's going to give us some energy back. This is going to be an exothermic. We get a return on our investment in terms of a lower potential energy. Typically, gaining an electron is an exothermic process because we make a bond. In some cases, this electron won't stick into an atom, and that's not going to end up happening. But in this case, it is, and in almost all the cases in AP chemistry, the electron affinity is going to be an exothermic reaction. But now we've got our potassium ions and our chloride ions. They're ready now to stick together. In fact, no, they are not going to be here separate for a fraction of the second. They're going to have the positive Coulombic and negative attractions come together and snap back together to make a huge exothermic reaction. Now I'm going to put that there, and they're definitely exothermic. Now, in terms of relative amounts, we know this reaction is going to have to be our V, which will be positive, our W, that's going to be positive, 1/2 of our X, which is positive, and then a negative Y and a negative Z. But do these reactions add up to make our final product? Let's see. Find out if adding these 1, 2, 3, 4, 5 steps produces this final reaction for the production of potassium chloride. Well, we've got our potassium solid here. That's what we want. But this, if we add things together, would give us potassium gas, which is not in our net equation. But not to worry, because there's a potassium gas here on this side that'll cancel out. So our net equation is not going to have any potassium gas in it, which is good because it shouldn't. How about potassium ions? Well, there are no potassium ions in our net reaction, but here they are as a product. But again, look, we have potassium ions here as a reactant, and they get canceled out. So we just have potassium solid turning into potassium chloride. Well, what about our chlorines? Indeed, we have our half chlorine gas, which is certainly desired here, but we don't have any chlorine individual gas. So let's see if that cancels out, because we did have that half, making it just one chlorine gas. That cancels, and our chlorides cancel too. And look, one electron, that cancels. So indeed, adding these 1, 2, 3, 4, 5 reactions produces our net reaction, and this summation of these actual enthalpies will produce our final reaction. Beautiful. It's amazing this Haber process works out so neatly. Well, our net result is a negative 437 kilojoules per mole. That's a lot. So this bonding of the potassium and chloride, this release of energy, is going to be big enough to make up for our endothermic. And this is the net reaction. And this explains all of it. This explains how we can figure out and how to analyze taking a metal solid and chlorine gas to make potassium chloride, our beautiful potassium chloride. But of course, you're not going to make potassium chloride using metallic potassium and dangerous chlorine gas. All the potassium chloride we get, we end up finding as a mineral. You can see what potassium chloride is. It's just a plain white salt. In fact, it's usually found with sodium chloride. It's an essential nutrient. You'll find it in your foods. It is derived from a mineral which is called sylvite. And here's a picture of some sylvite. It's sort of pink because of some ferric impurities in it. When lakes evaporate and oceans evaporate, you get salt left behind in great salt beds. The last salt to be found with the evaporation of oceans is the potassium chloride, and it makes this beautiful sylvite. Right now, one of the biggest formations or highest concentrations of sylvite is in Saskatchewan, Canada, where Saskatchewan considers it to be their mineral. And it's actually named after a chemist by the name of Sylvius de Libaud. And there's their sylvite, the major source. It gets purified, of course. They dissolve it and then get rid of all these other impurities. It's used medically. In fact, surprisingly, it is one of the 34th most prescribed medication in the United States. You need potassium ions in order for your nerves to work. And if your potassium balance is off, you can end up having nerves that trigger your heart not work. So it's essential that you have the right amounts. Here they got some ampules of 2 molar potassium chloride that they'd inject if you end up having too little potassium in your bloodstream. So here's potassium chloride, a essential electrolyte that is made from potassium metal and chlorine gas. Okay, that's the multiple choice and the chemistry behind it.